So today's lecture is sort of how you use what we did last time. Right? Last time was all about drawing samples from various probability distributions. And here are ways you would use those samples you drew. Right? So this is the focus today. And of course, this has already sort of been talked about a lot. Like we've heard the term Monte Carlo a lot. And this is sort of to give you some foundation. Okay, so we're thinking that samples x1, x2, etc. are independent random variables taken from some distribution f. So just to connect to Eric's talk, he had some distribution, some underlying distribution he didn't know. Getting those samples was a ton of work. Right? It took these huge weather models to do it. Right? So we don't often have the luxury of knowing f, but all of the formulation, we're going to assume that we have some function we can see, we can write down. All right, so given some other function g, we can define this quantity we'll call capital G, which if x was data, we would call this the sample mean. Right, so I'm taking each of my random variables, plugging them into my function g, taking the average. Right, so this capital G is like a sample mean. We want to use some of our properties of expectation from last time to take the expectation of this and show that actually the expectation of g is the same as the expectation of little g. Okay, so I take the expectation. So that means whatever is in here, I plug it in there. Expectations, this is where we're using some of those properties from yesterday. Expectations of linear operator. Right, so the constant can come out, it can go inside the sum. Right, now the key here, I guess two keys to get from this step to here, is that all of these are independent. And they're actually independent, identically distributed random variables, meaning they all come from f. Right, so you'll see that combination of words a lot, abbreviated IID. Independent, identically distributed. Right, so they all come from this distribution. So if I take an expectation of one of them, it's the same as all the others. Right, so if I take the expectation of each of these x sub n's, I get the same value. And it's a number, right? Remember, an expectation gives you a number. So I have a number, I have the same number, I have n copies of it, so those n's cancel and I get back this expectation of g. Right, and really, this is the thing we're looking for typically, and this is the tool we're going to use, this estimator to get that. And we're also interested in the variance of g, the variance of capital G. So we can write it like this. I'm going to leave it as a homework exercise. So Ahmed told me I was not giving enough homework. So, so you can blame him. That we'll get this factor of 1 out of n squared coming out if we take the variance of each of those small g sub n's individually. But now if we're here, if you buy that, and here so a hint on the homework, you'd have to use that idea yesterday that these are independent random variables, right? Yes.
Second equation, suppose it is 1 by n solution n equal to 1 to expectation of dx.
Yes.
When we are expecting, it can be the mean of dx.
Yes.
1 by n solution can help in that formula. Are we making considering dx as constant?
I'm sorry. I just can't quite hear you.
When we are considering expectation of dx, so when we know expectation of dx is 1 by n summation again of dx comes.
Here. Yes, okay.
So in that case, we are having more 1 by n.
I don't think I understand your question.
I think
How did I get from xn to x? So x could be any of these xn's. They're all the same. They're all the same. They all come from the same distribution F. So I could have left the n there, it would be equivalent. Yeah?
I think maybe the doubt is in the expectation is with respect to the function f. So the expression for this expectation, the one that is inside the summation, is integral gx fx dx.
Yes.
And the same thing on the left. So left will be integral, the whole thing in the square parentheses multiplied by f of x dx. So I just trying to now the variable. Yeah.
And actually, we'll get to this. Well, I guess before we get to that, is that okay? I mean, is there still confusion? So every time you see an expectation here where we're thinking about x being continuous random variables, that means there's an interval involved. Right? That means there's an interval involved.
Yeah, I think you make just one thing.
Yeah.
I think the E symbol here is not the sample E. The little n labels the samples.
Yeah.
And the E is not the sum over sample and divide by n.
Right.
So I think that may be confusing. The E is expectation with respect to f, whereas the sample mean is what's inside the parentheses, the square parentheses.
Right.
E is not a sample.
E is not the sample mean, no. So E, and actually, I'm going to introduce this notation in a second, but I hadn't yet. So E of anything is going to be the interval of that thing, dot, times f dx. And the distribution we're thinking it's associated with is, we'll soon I'll switch to this notation where I'm labeling the expectation. And both of these, right, I'm taking expectations with respect to this distribution f. Okay. So here we can write down the variance of G. I'll leave this exercise to you. And then we have the same game where I have 1 over n squared I could pull out in front of the summation. The variance of G is a number, right? I have n copies of that same number because these x's are identically distributed. And so I get that factor of n from the summation, canceling one of those. So I'm left with 1 over n times the variance of G. So as our number of samples goes to infinity in this estimator, the variance of our estimator, capital G, is going to go to 0. But if you've taken a class on statistics, this is the tool you use constantly. Right? The more samples we have, our sample mean is inherently a random variable here, right? Because it's taking a random. So this is, you shouldn't think of this as a mean or an expectation at all. You should think of this as a function. This is just a function of x of n. Right? That's the way to think of it. That's a better way to think of it. So G's capital on purpose because it's a random variable. Okay, other questions before I get on to the second slide? Okay, so here's what I just wrote down, basically, that if I take the expectation of G with respect to x, it's just this integral. And we just saw, right, previously that these two, the expectation of the estimator is going to be the same as the expectation of G, which is the thing we want. Well, if that holds, right, if these things are equal, then my estimator, right, my estimator G, well, that's going to be approximately the estimator G whose variance is going to 0, right? So it's getting closer and closer and closer to this mean, to this expectation. It's going to be approximately this integral, right? And this is Monte Carlo integration. So I have the integral of some function. I could actually do this for any integral I like, but we often think about it as coming from somewhere physical where we have some underlying distribution. So it's the integral of the product of whatever my function is and the distribution we're interested in. And that's just going to be this sample mean of the random variables coming from F. So this is where we need the last lecture. Right? I need to be able to get these samples from whatever distribution F I like. Once I have them, I plug them into our function g that we're interested in taking the expectation of. Right, so this is Monte Carlo integration in a nutshell. So this is sort of one case I'll be talking about. And in some ways they're the same thing. They're not different, but it's useful to think about them differently. So I'll be talking about this case where we're interested in estimating the mean or some quantity that really depends on the mode, sort of the bulk of the distribution. Another common case would be where we have our function g is 1. Right, so that gives us just the probability, right? I have g is 1 right there. Yesterday, this was our definition of probability that x is bigger than a. So that just gives us a probability, but then our Monte Carlo estimate's exactly the same. Right, I have 1 over n. I plug my x into g, but g is 1. So it doesn't matter what x I plug in, I get 1. And then I count them up. The difference between these cases is F is going to give me samples wherever there's density in F. Right? This is what we saw yesterday, or 2 days ago, I don't remember. So this is what we saw. But now if I'm interested in the probability that x is bigger than a, well, maybe a is here. I'm going to get a bunch of samples that don't hold, right? That where x isn't bigger than a. So really what I'm doing here is I'm counting the fraction of samples I get where x is bigger than a. And we can do this by something called an indicator function. You'll see some different notation for an indicator function. It always the same thing. Sometimes you'll see like a capital 1 or an I that looks like a real symbol, but an I instead. Okay, any questions at this point? Expectation exactly for n going to infinity. So this also holds then if we think about instead of our random variable x looking at the sample mean, we have this capital G. Right? The same thing holds. So this says as n goes to infinity, the sample mean G, which is a random variable itself, is going to converge to this integral. Right? So if we take enough samples, Monte Carlo always converges according to the law of large numbers. The problem is what's enough, right? That's definitely the problem. Okay, so if you haven't taken a graduate probability class, this is a really ugly thing, right? You have inequalities going different directions. So I just want to forget the inside for now. And I have the probability of something is less than or equal to delta. So what can a probability be between? What values? 0 and 1, right? Those are the options. So if we're thinking the probability of something is less than delta, we're typically thinking delta is small. Right? We're typically thinking delta is small. So the probability of something is small. And this is just a really useful statement. We'll talk about more to understand the inside part. And it's not, but it could be called the fundamental theorem of Monte Carlo methods because it estimates the probability of large deviations from a Monte Carlo sample. So here, let's write in G and the expectation of G. And the only other thing I'm going to change is I'm going to take the square root here to be a square there. All right, so we're rewriting this. This side's the same, except I moved the square root over. And now I'm just replacing these pieces by their definitions. So G was our estimator, so it's 1 over the n, the sum of small g of xn. And the expectation of G, well, that was the same as the expectation of little g, which is this guy. So let's just focus on this piece. So this piece says, what's the difference between my estimator and the thing I'm trying to estimate? Right, so this is really our error. This is our error in our integral if we do a Monte Carlo integration. So if we come back here, I probably didn't leave myself room. We have probability that our error squared is greater than something. Right? So basically this is sort of giving us a bound. It's saying that the probability that our error is big is small. Right? So big is sort of a requirement you hand me when you tell me to do the integral. Right? How much tolerance can you handle the integral being off by? Right? That's going to be this number. Right? That's going to be your error. And the rest what we have here, right, this is sort of what we have to work with, right? So this just says the probability that a sample calculation and the exact solution differ by more than this quantity, which will specify a numerical value what that needs to be, the probability of that can be no more than delta. Right, so you want the probability that your error is large to be small. That's what this says. Okay. So for some specified certainty, so I want a probability of 0.99 or 0.99, something good, right? I want to say this with confidence. There are only two ways we can manipulate this error term, right? So with a certain confidence, so this delta is fixed. The only thing that's not fixed are the variance of g and the number of samples we're taking. Right? So if I want this to be smaller, there's two options. Either the variance of g is smaller or n is bigger. Right? Those are our options. That's what we have to work with. Right? So when I think about in my kernel method to calculate an integral, it's just going to be some integral of some function. We can actually do this for any function, and there's actually a whole well, maybe this is something I'll tell you about later. But I can just think about integrating any function. And we get to break it up as we choose. So physically, it might come to us as g times f. But we can break that up as we like. Right? So I'm going to break up my integrand h into g times f, the product of two functions. F has to be a distribution. Right? So, and what properties does a distribution have? We should go back. So two properties that we care about. Does anyone remember? Independent. No. So I think you're thinking deeper. So I give you a function, any function. You tell me if it's has to be 1, right? So that was one of the things. What other property did it need? Can't be negative, right? So we need a non-negative function that integrates to 1 over whatever your domain is. Okay, so here's an example. So you think about how many samples it takes to have a 99% probability or 0.99 probability in calculating this integral. A 0.99 probability with an error of 0.1, right? Those are two different things. It's easy to get confused when you're first seeing this. Both of these things are prescribed. For this example, my error is 0.1, and there's a square there, so this term is 0.1 squared. This here, if we want a probability of 0.99, we want the probability that this doesn't happen, which is what this is saying, to be 0.01. Okay, so that gives us a delta of 0.01. And now we need to rewrite x cubed as a product of two functions. And we need the second choice here to integrate to 1 from 0 to 2. So let's think about two cases. So we can say f is uniform, right? And we saw last time a uniform distribution is constant over the domain. And it has to integrate to 1, so if the domain is too long, it has to be a half tall. And that's going to leave us with twice x cubed to get back x cubed as an integrand. Right? So a half times twice x cubed is x cubed. The other case we'll think about is taking our f to be 3/8 x squared. Right, the 3/8 isn't random there. I chose that, so the integral of 3/8 x squared from 0 to 2 is 1. And that leaves us, right, I need this product to be x cubed. So we'll look at those two cases. Right, remember what we're asking for here is how many samples are we going to need, right? How many samples will we need to take? Okay, so really what we're asking for is this error term, or this error squared term, the variance of g over delta n, to be less than 1/10 squared. So we need to calculate the variance of g and solve for n. Okay, so this is another homework for you. For those two functions with their associated distributions, you can write down the integrals, or just integrals. They're not actually even that hard of integrals. They're polynomials in this case. You can write down the integrals to calculate the variance of g in each case. If you do that, I took off any digits past the first, but you get about 20 times 10 to the fourth in the first case, and 1 times 10 to the fourth in the second case. So uniform was 20 times 10 to the fourth. That quadratic distribution is 1 times 10 to the fourth. Okay, so two questions. Why is this happening? Why are we doing so much better? Right? Why are we getting this lower variance? And what if we had a stricter tolerance? So I want to think about the second question first. Right, so if we had a stricter tolerance, right, so if I solve this for n, right, if I solve this for n, my tolerance is this term. Right, so if I take this from 1/10 to 100th, I square that when I solve for n. Right, so if I wanna go up in order of or go down in order of magnitude of my tolerance, I'm gonna need to go up in order of magnitude in I'm gonna need to go. I think I'm saying this poorly. It's not a hard calculation at all. So let's think about it. Right, so let's solve for n actually. So we have 1 over delta times 1 over 10 squared is going to be times the variance of g. And it has to be bigger than that. Right, so if I change this from a 1/10 to 100th, right, so that means I'm, instead of here this term, right, if I flip it over, I'm multiplying by 100. I change this to 100th, right, that means I'm multiplying by, what is that? So 100th squared, how many zeros do I have there? Huh?
4 zeros.
I go from 2 to 4 zeros, right? So the moral of this story is Monte Carlo is not very efficient, right? It's not very efficient. In terms of sampling, that's actually the key. It's not efficient in terms of samples helping us, right? More samples, we need a lot more samples to help us a little bit. Okay, let's go back to this question. Why do these variances look so different? Okay, so here's our integrand in both cases, right? So here's our uniform case. Here's our case where our distribution was 3/8 x squared. So this was what our integrand looked like. Here are our distributions. Here's some samples from each of these two distributions, these red dots. Right, so what we really want, right, well, we're calculating an integral. We want to be sampling where the integral has a lot of mass, right, where it has a lot of area. So these samples over here from the uniform distribution, they don't do us any good, right? They're wasteful. They're not really contributing to the calculation. I do samples from this guy, and you see it does a lot better. We get a lot more samples over where there's more mass in our function, in our integrand. Right, so we want to sample the domain where the integrand's big. That's sort of the first moral. And somehow, the magnitude of the variance is in some sense telling us how well we're accomplishing that goal with the F we're choosing. And we'll get to that. We'll talk about that more. Any questions at this point? Comments? Okay, so pros and cons of Monte Carlo. Cons, it's really inefficient, right? It looks like order 1 over root n. Right? If we relate that, so if this is an integration method, if we relate that to a grid-based integration method, that's order root delta squared. The very worst first numerical integration method you learn when you take calculus is what? What's the order? The first one you learn is order delta x. Right? You take your function, you approximate with it by a bunch of rectangles, that's order delta x. Monte Carlo is worse. So that's bad. Oh, and F can be hard to sample, right? If you have a physical F in your problem, maybe that's a hard thing to sample. Okay, pros. This error term is independent of dimension. The dimension of the problem doesn't turn up there at all. We have freedom to break up our integram like we like. So we have freedom to reduce the variance of G. And it's natural to set up stochastic problems as a Monte Carlo integral. Because sometimes there's really nothing else you can do. So I want to get to this idea of dimension. It's not that it's easy to do things in high dimensions. It's not. But if you think about, going to 2 or 3 dimensional functions and using a grid-based integration method, right? Those are incredibly expensive, and it just increases astronomically as you go up in dimension. So there's a whole field of study to do deterministic integrals using Monte Carlo methods. And that's called quasi-Monte Carlos. There are people that go to conferences on this, study this for their whole lives. And basically, they come up with, because this doesn't depend on dimension, if you come up with sort of very clever ways to sample F, Monte Carlo can work well in high dimensions. Okay, questions? Yeah.
So if you're given a function,
yes.
not an f and a g,
Right.
then, if you're given the splitting, then it's 1 over square root. But if you
Right.
choose one, then you can make it better.
Right. Yes, that's the moral. Yeah. So I guess I should have put that on the,
That's far from optimal.
right.
When you're saying it's inefficient,
Well-
grid-based methods in one dimension.
No, that's not necessarily true. What you're saying is not necessarily true. And we'll get to that. You're sort of forecasting what I'm going to talk about. Okay, so what I'm going to talk about is this idea of importance sampling. And again, we're going to think about it, it's the same method, but we're going to think about it differently in these 2 different problems we talked about. One where we're interested in the mode of the problem, and one where we're interested in maybe just part of the distribution. And we'll think about the mode first. So the key to efficient Monte Carlo is to reduce the variance. Right? Increasing the samples doesn't help us much, so we want to reduce the variance. Right? So the greater the variance, the more samples we need. And we've talked about that a lot already. So we're going back to our same integral. We want this expectation of G times F. We could estimate these with samples from any probability distribution we like. Right? We're not tied to the integram that's handed to us. And this was what Ahmed was just saying. So we're going to consider some distribution F tilde, and we're going to use our math trick of multiplying by 1. Right, so this is the same integral. It has the same expectation, because I multiplied by this choice of 1, F tilde over F tilde. And I wrote it this way intentionally, because now we can think about doing this with Monte Carlo, where this is the distribution we sample from, and this is what's left over. Right? Before we were thinking about the integral of G times F, we sample from F and plug into G and take an average. Here we're going to think about sampling from F tilde and plugging into this quantity, which we define as G tilde. Right? Right, so we could sample, I mean here we're still free to sample from whatever we like. If we sample from F, these guys go away, it's just what we've been doing. If we sample from F tilde, now what we plug into is G tilde, which is our old G, times the ratio of these probability distributions. And the Monte Carlo error is now determined by the variance of G tilde. Okay, so I've been pretty good about putting the distribution on the expectations. I should probably put it on the variance too. So this is the variance with respect to F tilde. Right, so remember, and this maybe looks messier because there's more in it, but it's the same definition of variance we saw in the very simplest case in the last lecture. I have the expectation of the thing I'm interested in squared, so all of these terms are squared, integrated against the distribution we're sampling from, or the distribution that we're taking the variance with respect to, minus the expectation squared of G. Right, so this is our variance of G tilde. This is what we want to minimize. Right, we want this to be as small as it can be, because the smaller it is, the better our Monte Carlo is. Right, but keep in mind, I've said this already, but this is really important, the expectation with respect to F tilde G tilde is the same as the expectation with respect to F is G, and that's all from this statement. Right? If this is G tilde and I sample from here, I can get this expectation of G tilde with respect to F tilde. Okay, so we want to minimize the variance of G. So that means we're looking for a function F tilde. We don't know it yet. We don't know what a good one is, but we have an idea of what a good one is. Right? So we kind of want it to look like the thing we're trying to integrate a little bit. Right? So I want an F tilde such that this variance is minimized subject to F tilde being a probability distribution. So let me go back for a second. The variance actually had two terms, but this term is the square of what we're trying to calculate. And this is a number, right? So there's, I should say, because these are equal, this is a number independent of which F tilde you pick. It's just going to be the expectation of G with respect to F. So to minimize this variance of G tilde, really we're minimizing this first term. Okay, so we've already seen, right? We've already seen some optimization this week. So we've thought about minimizing something subject to a constraint, right? And this is actually a very similar problem because this is also a functional, right? For a function, you put in a number, there's some rule, you get out another number. For a functional, you put in a function, there's some rule, you get out a number. Right, so here, really this thing is a functional over here if we can put in different F tildes, and we want to minimize that functional subject to this constraint. So what method did Rarahan use? Does anyone remember what it was called? Lagrange multipliers. So we do this with Lagrange multipliers. Right, and this is a calculus of variations problem as well. I'll leave it to you to at least formulate this as a homework problem. If you're familiar with variational calculus, do it. It's actually a pretty easy problem, but certainly you can formulate it. Okay, so this can be solved by Lagrange multipliers, which gives us this optimal F tilde. The F tilde should be proportional to G times F. Okay, so two ideas. Is this reasonable and is it useful? So these are the questions we want to ask ourselves. So is it reasonable? Yes. If we choose this F tilde, we get a variance of G tilde is 0. That's great. That means one sample, and you get the right answer. Okay, that's too good to be true, right? So is it reasonable? No. Because F tilde, to normalize it, we said it was proportional. To normalize it, we need exactly the integral we're trying to calculate. Right? So it's optimal, but it's also unknown. right? Because in a real problem, we wouldn't know this integral. Okay, so is it reasonable? Yes, and kind of no is probably a stronger thing. Is it useful? And is it useful is yes. The general goal is to make the importance distribution F tilde look like the integrand. Right? If it looks like the integrand, your variance is going to get closer and closer. It's going to get smaller and smaller. Right? Smaller and smaller. Okay, so here's just a cartoon. This blue curve, this is the function I wanted to integrate. Here's some importance distribution that I picked that I thought looked pretty good. You can see the samples off this distribution, well, they hit where the integrand's high. Right now, if I take the ratio of that integrand to the sampling distribution, I get something, and let me back up, because I don't know if I emphasized this. So this is my integrand, this is my sampling distribution. I'd like that ratio to look like 1, but I'd like it to look constant. If I take the ratio of this blue integrand to this sampling distribution, I don't get something constant, but it's a little bit constant and it's not too big. If I go to a bad case, so clearly this is not a good distribution for this function. Right? I'm not sampling over here barely at all. So if I go to this bad case, and I look at the same ratio, look at those numbers, that's huge. Right? So this ratio of the distributions is really what we're trying to minimize effectively. We know the answer, it's just that we don't know the answer. Right? Because the optimal solution is the problem we're trying to solve. Right? So we're caught in this circle. So let's look at an example. So we're going to consider, and I should say this with a caveat, if you know some more sophisticated probability, and when we're in this problem where we're looking for expectations, for things that really depend on the mode of the distribution we're interested in, there are more sophisticated ways to choose an F tilde. Like that's sort of beyond the scope of what we were able to cover in one lecture yesterday, or 2 days ago. But the idea is still sort of the same. So I want to go through choosing a good one for this integral. Right, we're thinking about it coming from an expectation. It doesn't really matter if it did. But we're just interested in an integral from 0 to 1 of cosine of pi over 2 x. This is a very easy problem. There should be an x right there. Okay, so this is the integral we're interested in. With anything else, when you're learning a new technique, you want to practice it on problems you know the answer to, right? Before you try it on your problem, which is interesting because no one knows the answer, you want to test it out on a problem you know the answer to. Okay, so first we'll pick our F tilde to be uniform. Right, so what does this mean here? So, okay, so the x appeared there, although it's in the variance term, but that's okay. So if we pick this to be uniform, that means that there's this x in there, and I multiply by 1 and divide by 1. Right, so my uniform distribution, the function just equals 1 over this domain. Okay, now if I look at the variance, right, and I actually do the variance in the x cubed case, it's going to be a calculation just like this, right, so you can do it for x cubed. So here I have the thing I'm interested in squared, I'm taking the expectation of times the distribution, which is 1, minus the integral we're interested to begin with, squared. Right, so we do this for this case. And again, remember, when we were looking to optimize it, this is all we can really control, because we don't know this, but we know it's constant. So we look at this case, we get a variance of 0.09. And remember, so usually uniform is not going to be your best bet. It's easy. It's the easiest, right? What do you do? I want to do this with Monte Carlo. I draw 100,000 uniform random variables. I stick them into cosine. I take the average. Right? That's Monte Carlo here with uniform distribution. All right, so let's take a better F tilde. We want an F tilde that looks like the cosine of pi over 2 times x. So I could sort of say, well, what would I get if I expanded the cosine of pi over 2 times x in a Taylor series? Right, so it would look like this. And let's just think about taking the first 2 terms. Right, that would maybe be reasonable. So this suggests that, well, I'm going to take these terms, I need to normalize them. So I'm going to multiply by some alpha so that this integral is 1 over alpha. Right, so when I integrate this thing, I'll get 1. But there's a problem here. Right, does anyone besides Amit see the problem? I think Amit sees it. He looked like he saw it. Okay, so there's a problem with this choice. So I hand you a function. You tell me if it's a probability distribution or not. Right? It already integrates to 1. What else could go wrong? Could be negative, and it is negative on this domain. Right? So I have, a little bit bigger than 9/8 there. So I have a 0 between 0 and 1 of that distribution. Okay, but again, we're looking for something that looks like our integrand, right? So let's try this. Let's take the 0 out of that domain. Right, so we'll look for an f tilde that's alpha times 1 minus x squared, an alpha of 3/2 to make that integrate to 1. We do this, we get a variance of 0.00099. So just by choosing a better f tilde, we reduced our variance estimator by a factor of 100. Right? So we made our Monte Carlo integration 100 times better, 100 times faster. Okay. Questions? Comments? All right, so I just want to sort of talk about, yeah. Right.
To the problem of doing a quadratic. We need to normalize this actually.
We need to normalize it.
The f tilde, so you need to do either 1 minus x squared.
Yes, yes.
So you either you have a ready bag of functions that
Right.
integrates to 1.
So this actually, okay, so let's think about this more, because Amit makes a good point. When there's this issue of, there's all sorts of f tildes you could pick that would do a lot better than uniform. A lot of them, an infinity of them. This one should do better. It certainly seems simpler to work with. One thing though, if I want to sample this, I have to integrate it and invert it. I integrate this thing and I end up with this cubic. I'm lazy, I don't want to invert a cubic. That doesn't seem like, that's not what I would choose. Right, so there's, you have to sort of weigh what's important to you. Right, is it sort of efficiency of you finding something that works, or efficiency of the computer? Because if you're okay with your computer running for an hour, who cares? Right? You do something that's simple that you can find that works. But that is the balance where we'd always be playing here. All right, so you just want to think about Monte Carlo versus grid-based methods. So again, this is the interval we're looking at. I have these evenly sampled. I mean, I'm taking them at grid spaces. Right, so this is what they look like. Here's what my grid looks like for a midpoint method. And what does midpoint method do? Right, it says, well, I go to each of those xn's. Right? I build a little rectangle that's with delta x. I evaluate the height of my function to give the height of the rectangle. I add up all the rectangles. I get an approximation to the integral. If I choose an f tilde to be uniform, this is what we get. So this was the same number of samples. I don't remember how many it was. But just visually, you can tell in one dimension that a grid-based method is doing better. Right? It's definitely sampling this curve better. But if we're looking at uniform, really our approximation, we're doing the same thing. We're doing this weighted sum of function evaluations. That's numerical integrals, a weighted sum of function evaluations. Here we have a weighted sum of function evaluations. What's different about this is where you evaluate the function. In Monte Carlo methods, we choose that randomly. Grid-based method, you tell me where to sample it. Okay, so where is this B minus A coming from? Because otherwise, if that wasn't there, this looks like Monte Carlo, right? Drawing from uniform. Any ideas? So if it's uniform, let's think about this problem we have up here, right? It looks like A and B are minus 5 and 5. If it's uniform, so my domain is from minus 5 to 5, so what does the height of my uniform distribution have to be? 1 by 10, right? I have 10 width, 1 by 10th height for my uniform. Right? So I have to multiply, when I'm actually doing the integral, I multiply and divide by this 1 by 10. I sample from this distribution that's 1 by 10, so that doesn't show up in my Monte Carlo. But then I divide it by this 1 by 10, which turns out to be multiplying by it. Right? So really the idea behind Monte Carlo integration and grid-based integration are the same, right? A sum of weighted function evaluations. Okay, so we sort of talked about the ideas of importance sampling. How do you actually do it, right? How do you do it in practice? So again, we have our favorite integral of the day. We have some F tilde. We've done some work to find a good F tilde. We've done some more work to be able to draw samples from it, perhaps. And now I want this estimate, right? And these two estimates, or these aren't estimates. I want these numbers, which are the same. Right, I can approximate this one with this estimate. Right, so remember what I did here, right? I divided by F tilde and multiplied by it. So now for Monte Carlo, we're drawing samples from this F tilde. The one we divided by becomes this function we have to evaluate. Right, so it looks like Monte Carlo if this term wasn't there. Right, in this term, so we actually take our samples and plug them into our original probability distribution function and our biased or importance probability distribution function. Right, so you take those numbers and plug them in. We take that number and plug it into G. Right, we sample more, we take an average. So this ratio of distributions is called the likelihood ratio. And really how I like to think about it is that for every realization, it sort of tells us how likely would that realization have been. So it's coming from F tilde, but how likely would it have been if it had come from F? Right? We're getting it from somewhere else, but how likely would it have been had it come from our original distribution? Okay, so now we're going to think about G being a function of many random variables. This is just really a note. This is sort of a note on, it's not really part of the story, but it's a note on importance sampling in multiple dimensions. So and with a caveat, choosing the importance distribution in multiple dimensions is hard, right? And it's very problem dependent. But how do we do it in practice? So if I have my random variable is really my function is really a function of many random variables and they're independent. Then remember, if they're independent, we had this property, that this joint distribution was really the product of the individual distributions, if they're independent. Right, so this joint distribution is the product of the individual distributions. The same for F tilde. So our likelihood ratio, when we're in this multi-dimensional case, is just a product of likelihood ratios for each of the individual samples, x1 here through xk. And just a warning, in practice, these likelihood ratios can be very small, and it's often not a good idea to multiply a bunch of very small things together. So numerically, you want to be careful with that. Okay, so we talked about, what we're doing is the same, but sort of the motivation behind what we pick is different in these two different cases. The cases where we're interested really in the mode of the distribution, right? And that would always be the case if we're interested in expectation, right? The second type of problem, remember, was this probability that x is bigger than a, right? So generically, Right, this was again our definition from the first lecture. It's just going to be the integral from a to infinity of our distribution, whatever x is drawn from. To do that, we draw a bunch of x's from our distribution, so we simulate these x's, or they're the results of computer code, or someone hands them to you, however you get them. And then you say, well, did this event I was interested in happen or not? Right? And you think about this, right? We've all done the simplest Monte Carlo, right? Flipping a coin and counting heads and tails. Right? Say you're just interested in heads, right? So let's probably heads. You don't believe the coin. Let's probably heads. So you flip it, you flip it, you flip it. You count how many times you're flipping in total. Every time you get a heads, you put a tally mark. Right? That's exactly an indicator function. And then you divide by the total number you take, and you get an estimate for your probability. Right, so it's the same thing for a continuous problem. Right? This indicator function just tells us if we're in this region of interest or not. So remember, it's going to be 1 if x n is bigger than a, and 0 otherwise. Okay, so just like our other case, for the case where we're sort of interested in the probability that might not be too close to the mode of the distribution, or the main mode, this is still guaranteed to converge by a law of large numbers. Law of large numbers says if you take an infinity of samples, this will converge. So that's good theoretically, but practically a law of large numbers isn't useful at all. Right? In practice, if this number A is much, much bigger than the mean of your distribution, it's not going to converge. You're going to take samples and samples and samples, and it's not going to converge. You're not going to get an estimate. If you could take infinity, right, you would get it. The law of large numbers tells us that. So we're going to think about this with this case of rare events, where we're sort of far away from the mean, this area where we're looking for the probability. And there's no definition of a rare event, but loosely you hear about probabilities less than 10 to the minus 6. Loosely. So things less than 10 to the minus 6 get trickier to calculate. You can say, oh, I could do that. Well, then do 10 to the minus 10. Right? Whatever you say you can do, I can give you a worse problem. Okay, so the idea here is to use importance sampling again. And now, though, right, I said if I just wanted, and think about what the expectation of this thing would be. Well, it'd have to be 1, right, because this is a probability distribution. I integrate from minus infinity to infinity. So if I sample directly from my distribution and do Monte Carlo, that's perfect. I'm sampling the mode. But if we're interested and A is really far away from the mean, maybe our f tilde doesn't really look like this function, right? It doesn't look like our distribution. Our estimate's going to be the same if someone gives us a good f tilde. Right? I'm going to have this indicator function, and I have to weight it by the likelihood ratio. Same as for the other case. Right? I have my function here, which is 1 in this case. The indicator function really tells me about this limit. Right? It tells me about that limit in this problem. And so I weight my events that happen by this likelihood ratio. Okay, so how do you pick f tilde? So this is the simplest example. So say you want to flip 100 coins, and you want to know the probability of getting 70 or more heads. Okay, so again, this is a problem we can do by hand. If you've taken a probability class, at least set up what this is. Right? At least write down the expression. You might, it's evaluating the expression is harder than writing it down. But for homework, you should write down the expression that would give you that for this problem. Okay, so importance sampling in this case means using a weighted coin, right? If I flip the fair coin, I'm never going to see 70 heads. Right? You could have your little brother flip it for the rest of his life. He's never going to see 70 heads. Or maybe he sees it once, maybe, right? So what? He sees it once, then his probability is 1 over however many samples he takes. He's never going to see it again for the rest of his life. Right? So to get an estimate, you need n squared of what you're interested in to get the estimator to converge without fooling with the variance. So our idea is to use a weighted coin. So I want to get heads 70% of the time. I'm going to use a coin that's weighted to give me heads 70% of the time. Right, so the probability that I get heads is 0.7. The probability that I get tails is 0.3. And now I need these likelihood ratios to remember the idea of the likelihood ratio. How likely would heads have been if I had flipped a fair coin? I'm getting heads from my bias coin. How likely would that have been if I had flipped a fair coin? Right, so it's going to be the ratio of those two probabilities, so 0.5 over 0.7. And here we can think about this. Right, this is correcting our. We're using this bias coin, this weighted coin. This likelihood ratio is correcting for our bias. Right, now I have a probability of getting heads 70% of the time. Well, when I'm going to flip this bias coin, sometimes I'm still going to get tails occasionally, right? 30% of the time or so. And so there I need to calculate. I have a different likelihood ratio for that outcome, right? Because remember, the random variable you simulate goes into this ratio. Here, there's only two options. Right? For a continuous problem, you'd have an infinity of options. Okay, so this says, well, and this is funny, so we'd expect this to be smaller for heads, right? We don't want to, if I didn't correct the likelihood ratio and I just tallied heads and tails, I count heads way too much. Right? This corrects our counting. But now, I made getting tails less likely. So if I actually see it, my likelihood ratio is bigger than 1. Right, so correcting with the likelihood ratio gives us statistics for a fair coin. We could speed up a simulation by more than 10 orders of magnitude. Right, and part of the reason we could do that so well is because we knew what this bias distribution should be optimally. Right? It really looks just like the problem we want to do. Any questions on this? Comments? So let's look at an example from what I would call a real problem. And you say, oh well, that still doesn't really look like a real problem because I'm just calculating the probability of a normal distribution, right? So I'm going to say z is normal 0, 1, and we're interested in the probability that z is bigger than 4.5. Right? So and if you've ever taken a sort of an intro level statistics class and you have the book, right? The end of the book is filled with these tables. It's filled with tables that are numbers just like this. Right? Because the problem with, this is sort of something I have sort of a philosophical hard time with at my university, is that for a statistics class, they do not require integral calculus, just one semester of calculus. So you think, probability and statistics, it's all about integrals. How could you possibly not have them know integrals, right? But practically, it's not an issue because almost all the integrals you encounter are ones you cannot do. You can't do them. Most of them. You just can't. There's no way to do them. Certainly no way you would learn in your second semester of calculus. And so instead, what there are is there's these lists of tables, right? And this number is on that list because this is an integral we can't do. And I was thinking about this. How it was done, sort of for sorry, there shouldn't be a period there. How this was done for the first statistics book that had these tables. And I think there must have been series expansions. I don't know. But anyway, so say we want to do this with Monte Carlo. So this is our problem, right? I want to know the probability that my Gaussian, my standard Gaussian, mean 0, variance 1, that the probability that random variable is bigger than 4.5. All right, so this is our Monte Carlo integration. It's 1 over n times the indicator function, which just means we're counting how many times it's bigger than 4.5 out of n samples, right, and looking at that ratio. And we'll say that's our estimate for the probability. All right, so and I just did this morning. So I took 10,000 samples from a normal 0, 1 distribution. None of them were bigger than 4.5 of 10,000. And in fact, the biggest one was about 3.5. Right, so this is even though you can tell this is a Gaussian, right, this is the simplest problem ever, this is a real problem in some sense, right? This isn't something you can do with Monte Carlo integration, with just sort of vanilla Monte Carlo integration. So here's just sort of a picture of our problem. So we have this normal random variable. This is what I'm drawing samples from. Right, when I drew them on my computer this morning, they all ended up in here. Right, the biggest one was about 3.5. Right, this line is at 4.5, and what this probability is really asking me for is the area under this curve to the, I guess, the right of this line. So you can't see it, but there's still some area under there. Right, so we're looking for the area under the curve to the right of this line. So of course, if I sampled from this normal distribution, I wouldn't expect to get samples there. So this is where we have to sort of philosophically, I mean, our methods are the same, but philosophically we're thinking about an expectation in using importance sampling different from maybe a probability calculation of a rare event in using importance sampling. Right, the goal is very different, so our tool, our importance distributions are going to look very different in those two cases. And I should say, just sort of, I mean, I guess I went into this, so my logic with the lectures I'm giving is to talk about importance sampling because it's sort of one of the fundamental tools used for particle filters. But how they're thinking about it is capturing the mode. So when I say this, when I'm talking about particle filters in the next lecture, that's what I mean. But this other problem is really interesting, and maybe it's useful. I mean, it has to be useful in data assimilation in some way, because we're interested in these rare events, right? We're interested in when we get a severe drought during the monsoon season. Okay, so instead of sampling from this standard normal, we'll sample from an exponential. Remember we saw an exponential last time looks like this. We're just going to move it over from the origin over to 4.5. Right? Because think about what's happening here, right? All of our samples are in here. They're all wasted. None of them are hitting our function where we're interested in it. So let's not sample over there at all, right? And here, and this goes maybe back to Amit's point, that this distribution we can work with. This interval we can do, no problem. This interval we can do, right? This is just to normalize it. I've moved it over to 4.5, and I'm only considering x bigger than 4.5. This is an interval we can do. This is also a distribution we can draw samples from pretty easily. Right, so now we've taken basically an impossible problem, and with the good choice of this f tilde, made it a reasonable problem. Right, and so we can't see this tail. I probably should have blown it up on a log figure. We can't see this tail, but this tail, what we kind of want is our importance distribution to kind of have the shape of the tail, right? Which effectively means, you know, this is a decreasing function, so effectively it means I'd expect sort of the action to happen right at this transition. Right, so I want to be sampling there much, much more. I want to be sampling there much, much more. Right, and we do this problem, again, now I don't, so really I should have this indicator function in there, but with the distribution we picked, we're not sampling. All of our samples are going to turn the indicator function on. Right, so you can think about the indicator function is there, but it's always going to be turned on because we're always sampling to the right-hand side of that line. Right, and then what we're doing is just taking the average of these likelihood ratios. Right, and practically, what are we doing? So say I sample 5, I plug 5 into my standard normal. I plug 5 into this exponential function. I get some number. That's my instead of a 1 for my tally, that's the number to account for this biasing. And we get a probability that's really pretty small. Okay. Any questions? Comments? Okay, so that was all I had. So I guess we have about 5 or 10 minutes left. So if there's any questions, we have some time to talk about it. Or questions from the tutorial is fine too. So again, I'll try to fix the typos I saw and send a copy to Amit. So this will be posted probably this evening.
How do we do this with application? I have data from an experiment.
Mm-hmm.
Data. I don't know what distribution it falls in. So how do I do it?
Okay, so if you have data, so there's a bunch of questions wrapped up in that question. All right, so if you have data from an experiment, say, or computer experiment or physical data, whatever, and you want to categorize it, that's really a different problem, right? Then you're trying to say what sort of distribution does this look like it comes from, and it's actually that's sort of what we're doing with data assimilation, right? Where we say, well, maybe if it's Gaussian, the Gaussian would look like this. And we haven't talked about the particle filter yet, but it's sort of what the particle filter tries to do, at least partially, right? Then it's also looking at weighting the observation in the model. But, so really, I mean, that's kind of a different question. But if I want to think about just calculating something with those numbers, well, you've sampled some distribution. So I don't know what the distribution is, but you've already sampled it. Right? If you have numbers, if you have data, you've sampled some distribution. Right? And next time, so I was going to have this in the talk today, but then everything's sort of gotten shifted back. So next time, I'm going to talk about sort of a way to deal with estimators of either samples or that taken samples, estimators of some quantity we're interested in, that taken samples or data, right? To give you a sense of how good that those samples or that data is. Right, so I'll talk about that next time, and that's something called the bootstrap. Any other questions? Yeah. Yeah. Is there physical significance of the ratio? So again, that's problem dependent, right? So if we were interested in a mode, that would be something different than here. That there's the same sort of thing. So this isn't something physical, but you can keep track of, I talked about this last time, you can keep track of, even when you're doing importance sampling, you can keep track of the sample mean, the sample covariance you're getting. And effectively, that coefficient of variation should be small and it should be stable. Stable is important. Right? It doesn't mean I could think about another problem where really, say I misread the problem and they weren't interested in this being bigger than 4.5, they were interested in the absolute value. Right? And I didn't know that. I didn't know I should have been looking over there. I would never get it. Right? I would never get it. And I guess at another point too, the sad thing, I mean, the sad thing, so not in this example I drew up, but because I cut it off at 4.5, so I'm not going to sample -4. But even Monte Carlo with a terrible choice of the importance distribution, if you take enough samples, will converge. Right? And enough then becomes astronomical. But by law of large numbers, it says eventually you will cover all of state space. Right? You will converge. So practically, the choice is kind of a hard thing to do and is really important in actually getting an answer. But you can't, and this is sort of where you can go wrong with importance sampling, right? Is I can do this problem where I say, I know what I'm doing, I've calculated all of this, and I didn't know there was a region of state space that I should have been considering, right? And that I mean, any of the tests you do, there's nothing that can tell you that you didn't miss some region in state space, and that's the sort of true in whenever you're thinking, whatever method you want to use, right? That's, if you don't know where to look in state space, where So this is a quote I saw, and when I saw it, it was attributed to someone, and then I wanted to use it, so I contacted this person. He said, no, it's not mine. Let me email. So then I didn't know. I mean, this is, as a graduate student, he's some professor in California, I don't know. And then he emailed his circle of friends, and none of them knew where it came from. Okay, but there's this quote that says, I'm paraphrasing, but says effectively that rare events, let me think about it before I butcher it. Right, so the probability of a rare event is small, of course. But a rare event is going to happen in the most likely way, right? If a rare event happens, whatever caused it to happen is going to be sort of the most likely combination of circumstances to make a rare event happen, right? And we could think about this if we go back to the coin problem. Right, so I'll help you with your homework, right? How do you calculate the probability of heads or more? Well, you need the probability that you get exactly 70, plus the probability that you get exactly 71, plus the probability that you get exactly 72, all the way up to 100. If you compare those probabilities, the bulk of that 10 to the minus 13 is in the first 1, 2, maybe 3. Right, so I could get 99 coin flips, that would satisfy my integrating factor, right? That would say, yes, I got more than 70, but the probability of that happening is tiny compared to what's actually really contributing to this calculation. So rare events happen in the most likely way. Any other questions? I'll have to find the exact quote. I don't remember exactly. Okay.
So I guess you could combine the important sampling and accepting. So this was simply taking the ratios and adding them all.
Right.
But then you could combine, take those ratios, take uniform samples, and depending on the ratio, maybe smaller or greater than combine, you accept the
I think I think the hard part of any idea like that is showing that it's ergodic, right? So I think people think about that, but if you ever want to mess with the formula, you don't know, right? That's the
It seems like in this case, all you needed to know to do the importance sampling was the question that you were asking.
and that was the sort of the moral of the whole talk, right?
So is that generally an importance sampling? That's what you need to know is the question you're asking, and then you can do it, and then you can...
Yes. Yeah. So you need some information to tell you about what you want to know, right? So for this other example, right, we said we want to integrate this cosine, well, not the constant, but the cosine of pi over 2x, right? And then we did uniform, and that didn't work well. And then we said, well, that integrand, we really want it to look like the integrand. The integrand in the region that we're interested in, right, which is sort of the last example said. So I'm going to come up with some approximation. How you come up with the approximation is totally up to you and problem dependent.
More than just the question.
Yes, generally more than just the question. But this would lead you back to thinking about, right, if you wanted for sort of a physical-based reasoning, if there is a drought during monsoon season, what is the most likely physical scenario to lead to that drought? How do you sample that physical scenario from, so you do need to know the problem, right, to have a sense of a chance. Right, and yeah, sorry. I mean, the hard thing is when you go to high dimensions, You could have all sorts of things that get you samples in the right region of state space, but there's no way to know that you found the most probable one. Or maybe I don't know of a way to know it. Maybe there's some theory on that I'm not aware of, but I don't know of a way to know that you found the most probable one. Right? Because it goes back to this question. You're really looking for the problem you're asking.
The whole idea of adaptive multi-causal is, so you're trying to solve, say, do this integral, and you see that collecting samples which are giving you very small values of the integral. You know that you're in the wrong part of the space. You don't shift somewhere else. So the whole idea of the adaptive multi-causal is use the past information in the multi-causal to change your F tilde, so that the adaptive multi-causal it changes the field at every step, and that you make it better and better based on the information that you have gathered in. So that it gets around this problem of, well, to get a good F tilde, you need to test F tilde 3 times that, which is what you.
But still, when you're in higher dimensions, to do that search of state space is non-trivial.
Highly non-trivial.
Highly non-trivial. Yeah. Well, it helps. I mean, if you have it, it helps. That's the. But that, I mean, that's something where, you know, if you have this adaptive strategy and you're starting somewhere in the right ballpark, you have a shot, right? I mean, I think that, I don't think it's that you shouldn't try, but.
For example, sampling that I did without adaptive,
Right. You have to have some sense of where to start, right? Lunchtime.
Maybe during the talk about